Thank you everyone for attending the lecture so far. So we are almost there. I have one more a lecture that is standard, and then we can. And I hope that I can finish the major of the material here, and then I can talk a little bit about the final exam format. And when or and also to arranging a time for the final presentations. Okay, so I think so far I received one results already. So if you have time to actually start to working on the final project, that would be a good time to start now. Okay, so today what I want to talk about is dynamics. Dynamics of porous media. Okay, so we talk about the pore mechanics a lot. Pore mechanics itself, including the quasi-static, static, transient, and dynamics. But dynamic is actually very important for many applications. Just like the single solid mechanics, we care about the dynamics when we consider the inertia force is big enough so that we start to care. Okay, and what it lead to is the relationships that we will have a PDE that would depend on the second derivative in space and also second derivative of time. Okay, does that make sense? So in the 1D analog, let's say I solve a boundary value problem. In the quasi-static case, what I would have is that I may have something like this equal to 0. Okay, does that make sense? Okay, so in the static case, like your Poisson equations. Okay, just a second derivative. Maybe I use more well-known notations. So maybe just temperature or whatever equal to 0, or some variations. The first derivative of some kind of conductivity parameter that are actually equal to 0. Something like that with boundary conditions. Okay, you see what I mean? So what it means is that you have to take two derivatives, right, eventually on the field. And the pattern that you will get here, if k is constant, and x is a profile, and this is your solution, it's just a straight line, right? If k is constant. Okay, it could be many different straight lines, but it will be just a straight line if k is constant, isn't it? Okay, your second derivative equal to 0. That means your first derivative is linear, right? Right? You see what? Sorry. Your second derivative is 0. That means that you have to able to take the first derivative, right? And then and if the first derivative is linear, then you would actually have a field that looks like this. Did I write it correctly? Okay, so now what happened to a transient problem? In a transient problem, I'm just using the 1D as an analog. I will start to have this term, but then that would be equal to some kind of time derivative. Okay? Does that make sense? Okay, first order in time, second order derivative in space. Okay, so what kind of pattern will I get? First, notice that if there's a steady state, eventually I can assuming that if this thing go to 0, I just get back the first case, right? Isn't it? This is actually usually the steady state equations if the solutions actually eventually have a steady state at all. Okay, does that make sense? Okay, but in time, then what will happen? Okay, if you consider a very short period of time, okay? So then what happened? Okay, so it depends on whether there's a parameter. Let's say I put a parameter k here, like permeability. Okay, if k is actually very small compared to the time, then this term will become bigger, right? Okay, so if this term become bigger, then what does that mean? Then your governing equation doesn't have, in that short period of time, doesn't have that much spatial relationships, okay? So they are actually like ODE moving independently, right? So in the transient problem, what you see is that, let's say I have a source turn in the Tasaki consolidation problem. Initially I have a jump, and then it go through time, and then eventually I just get a straight line moving to 0. Okay, so there's a boundary layer or whatever that are growing, in the sense that at the beginning, sorry, this is actually the solution field. So this is C, and this is the solution field here. And I should put C here. Okay, this is Tasaki's problem. Okay, at the beginning, if you actually swap the XY axis, I simply have 1 here and then 0 everywhere, or whatever. So, or actually, in this case, maybe 1 everywhere, and this, okay. Yes, and then over time, it actually changed. So what you actually have is a change of the behavior from ODE behavior to eventually the quasi-static behavior, okay? So the slope is actually changing over time simply because over time the relationship between this term and this term actually change, right? Okay, now this is actually one way to think about it, or you can think about it, there's a boundary layer that are growing. Okay, so at the beginning, actually, you only need to consider the jump for the Tasaki problem, and then in all the other space, there is nothing. We simply get a straight line, but then that transient relationships may change over time, eventually reaching the steady state. Okay, so this is another set of problem. Now, then what we actually want to talk about is finally this type of problem. I have a second derivative in space and second derivative in time. Okay, so now if you look at space-time in 1D, they look pretty parallel, right, to each other. Okay, you see what I mean? So what will happen in this case? Okay, so what happens is that if I have a pattern that look like this at time equal to some time, okay, what would happen after a given time? Okay, it will move towards one of the directions. In this case, it will be here because I'm actually moving in this direction. So I have this pattern are very different in the first and second case, in the sense that the pattern won't be getting smoother and smoother over time, okay? It's just simply moving, okay? This is actually making the dynamic problem much harder to solve, because you eventually don't have the smoothness that actually guarantee your finite element to work, right? So what are the common ways to deal with it? One of the common ways to deal with it is to add an additional term that are actually first order in time. Okay, maybe with a parameter d. So what will happen? So this is called damping in your structural dynamics. If you were damping, what happened is that you're still propagating the wave, but eventually all the kinetic energy would be damped out and you're moving back into this problem. Okay, without the damping, the energy is conserved, the wave will propagate infinitely. Okay, if you have a domain that actually prescribes d equal to 0, it will just bound back, have a refractions, and then keep bonding forever. Okay, so I just want to give intuitive descriptions about this big picture, because what actually happened is that the way that the solution field evolve over time would affect how you think about the discretization problem. Now then, this is also another thing for pore mechanics. In the pore mechanics, we have two materials that are actually bundled together temporarily, right? Okay, so how many waves do I have? Okay, so this is actually the answer, the study that are also done by Professor Beals on the acoustic of porous media. And in fact, you would actually observe a secondary wave that you won't otherwise observe in a composite, okay? So what it turned out is that there are at least two compassive waves. One is actually like the solid one, and another one is actually related to the porous media, okay? Now, let me come back to the balance equations because that one is actually pretty easy to understand. We have the balance of linear momentum, very similar to what we have. In fact, there's nothing that are actually particularly interesting. Except that there's accelerations here. Okay? Now, this accelerations is the acceleration for the solid part. Okay, now the question is that will the solid and the fluid have the same accelerations? They won't, because first of all, they have different density, and second, they may not need to move in the same trajectory, okay? So they in general difference. So this is a solid one. And then I can also add the fluid. Which, if you actually notice, I just rewrite the whole thing, but swapping the subscript and the superscript S with F. If I combine them together, the internal force that acting on each other cancel out. Hs plus Hf equal to 0, just like what we did previously for the quasi-static case. And then we reach the balance of linear momentum. The divergence of stress plus rho g plus 0 equals to, now not equal to 0, but the rho s as plus rho f af. Okay, this is pretty easy to understand. Okay. Sorry, and then plus also the rho s minus the rho fas. Sorry, this is actually not complete. Okay, so now notice that I did one thing here. Okay, I add and minus this term. Okay, basically essentially doing nothing, right? I add the rho f times as minus the rho f minus as. Right? Why do I want to do that? The answer is the following. I remember that I still have two trajectory S and also another trajectory rho F. Okay? However, when I model the material, I can only afford to have one reference frame. So in this case, again, I will take the solid or geotechnical engineering approach to take the solid film as my reference film, and then I follow the solid trajectory. Versus the fluid part, I will model in a relative term. And so consequently, I have AS plus rho F times AF minus AS. What is this? This is the rate of change of the relative velocity, okay? And why do I actually want to write it like that? Is that it's related to the Darcy's velocity, right? Okay, and why and how do I get this? What is the relationship between the Darcy's velocity and the relative velocity is that they're separated by the porosity, right? Okay. So porosity times the relative velocity give us the Darcy's velocity. Okay, maybe I write it like this. So the Darcy's velocity, I forgot what is the right notations, is actually the volume fractions of the fluid of the void space, and times the relative velocity, which is the absolute velocity of the F minus the absolute velocity of S. Okay, so if I take the time derivative and I would actually get the change of the Darcy's velocity would be actually equals to the rho F times rho F minus rho S. Okay, does that make sense? Okay, so now according to the chain rule, that lead to two different terms, isn't it? Right? Is it? The first term is the rho F dot Vf minus Vs. The second term is actually the rho F times Af minus As. Okay, does that make sense? A is just V dot, okay? Now, so if you substitute back there, it will give you the relationship rewritten in terms of the Darcy's velocity. Okay? Does that make sense? Okay, or in other words, AF minus AS is actually equals to V dot minus rho F dot Vf minus Vs divided by. Okay, so far so good. So this would be the new governing equations that we need to put into the final element, the first component of the strong form. Okay, balance of linear momentum. Now, let's say I compare, assuming that rho F dot equals to rho S dot equal to 0. Okay? Can you translate this to English? What do I mean? What does that mean? Yeah, incompassible constituent, okay, or the phase are incompassible. Okay, doesn't mean the matrix is that. So in this case, what is the balance of mass? Does the balance of mass affect by whether you consider the inertial force or not? Will it be affect? How many of you think you have a different balance of mass? Raise your hand. So how many of you think that you have the same balance of mass? Raise your hand.
The same as what?
But the balance of mass, without working on any derivations. Okay, just your intuitions. We might recall the balance of mass is divergence of V plus the divergence of the Darcy's velocity equal to 0. Okay, now can these equations apply both to the transient first order in time and also the second order in time without any change? So yes, actually they are actually identical. So in other words, the only part you change is this part. Okay, so this is the two governing equation you need. Okay, so this is actually not very complicated per se. Okay, you just need to think about this additional time. Sorry, there's an AS there. Okay, so now, but in practice, what is the complicated thing is the two things. How do I discretizing the space so that I can solve the dynamic problem? And also the constitutive law need to be changed. The constitutive law for the solid doesn't necessarily change if the material doesn't have any creeping or weight-dependent behavior. However, the Darcy's law need to take account of the inertia fluid force and then they need to modify it slightly, okay, to accommodating a dynamic effect that affect the seat gauge, right? You understand what I mean? Okay, so if the water are actually, so on the other hand, imagine that I have two water that are actually both have an upstream and downstream. Okay, so just a Darcy's velocity device, okay, one upstream, one downstream. One is that the ground is static and then you just move. And then another one, I'm shaking it horizontally. Okay, the one that shake horizontally and then the one that doesn't have shaking will not move down in the same speed, even in the vertical part. Okay, so this is actually the change of the constitutive law that we need to talk about. But before we talk about the constitutive law, let me first talk about the choice of discretizations that we need to consider. Okay, you see this mass term, okay, and this is the total density, and this is actually the density. Sometimes you simply put this term there and ignore this term. Okay, the reason is that you argue that the first term is bigger, and that's it. Okay, so is it better? Is it bigger? Usually they're bigger because first rho is actually, in terms of magnitude, okay, you can go into different directions. First of all, rho is actually higher than the rho f in generally speaking, because rho s is actually, the density of solid is actually higher than the fluid. Okay, otherwise it will be on the surface, just like ice. Ice is a solid that have less density than the water and it floats, right? Okay. Okay, so we will stick to a few choice, and in the literature, there are very, very rich choice of the governing equations that you can pick, and I just list some of them. Okay, so the first thing is that, let me make some assumptions. Let U be the solid displacement. Okay, and then I'll add something called big U, and I'm actually using that notation U just to honor the previous research that actually introduced the notations to be consistent with them. Is the fluid displacement. I don't know why they picked the big U as a fluid displacement, but I'm just simply using the same terminology. And then another choice that I would have is actually simply using the Darcy's velocity. And in this case, the terminology they use is the W dot, which is actually equivalent to what we use, the V overhead, which is actually the Darcy's velocity. Okay, and then of course there's a P equal to pole pressure. Again, this is actually only two-phase material. I don't add air there. If you want to add air there, that would also be very interesting. The retention curve in a dynamic regions also need to be changed. Okay. So why do I need this four ingredient is the following. In the literature, there are actually many different combinations that are used. So let me explain them one by one. Okay, so this is the four ingredient, 1, 2, 3, 4, and you can see that 2 and 3 are actually kind of related to each other. Whether you like to moderate in terms of velocity and displacement are actually your options. So usually 2 and 3, they don't appear together, if you can see that. Does that make sense? When you actually write it as an unknown, in principle, you can write anything as an unknown. You can even put stress as unknown. Okay, but for practical reason, no one have tried to put U and the fluid displacement and velocity, Darcy's velocity together, meaning that you either solve the Darcy's velocity or the fluid displacement, but not putting them both. In the sense that sometimes people would just forget about the Vs term, or we can argue. Let me talk about them one by one. The first one is the P formulations, okay, which is the most complete and most expensive. So in three-dimensional case, I have 3 degrees of freedom for the displacement. I have 3 degrees of freedom for the fluid displacement. I have 1 pressure, and in total, I have 7 at least. I'm sorry, at most, not at least, at most 7 degrees of freedom per nose. Okay. And the second choice is actually the U formulations. Actually, it attributed by, I think it should go back to Sean Perros from Princeton University. I think he derived it. And the interesting thing is that this one doesn't have P there. Okay, there's no pole pressure. Okay, so to write the balance of mass, that one is pretty easy, right? Do you think so? The balance of just divergence of U plus the divergence of U equal to, divergence of U dot equal to 0. Okay, or you can even take divergence of U plus divergence of U equal to 0. You don't have to take time derivative. Okay, but what is the difficulty? Is that I have to write the divergence of the Pi equal to 0 somehow without using the P, right? Okay, you see what I mean? So I kind of need the inverse of the Darcy's law, right? The Darcy's law gives us the gradient of P equals to what is the relationship between the velocity and the gradient of P, right? But now I only have U, then I need to somehow write the gradient of P, right? Okay, but is it doable? It's actually quite possible to do, but then you have to work on the algebra yourself, okay, to take out the P term in the balance of linear momentum. So this one, the advantage is that it's easy for the balance of mass, but you actually need to derive something for the balance of linear momentum. Does that make sense? Now then, there's a 3, and I think that you can actually see why. Okay, so this is actually the time integrated versions of the Darcy's velocity. Okay, I just use the UW formulations. Okay, so this one is actually give you a little bit more tools to actually using the Darcy's law more effectively, right? Okay, but then you have a difficulty of writing the inertia term, okay, if you don't have the relative term. Okay, so this is actually a particular fit for the deviation that we have with the balance law, where we already write functions as AF minus AS, right? Do you think so? Okay, so remember our right-hand side inertia force term is actually rho AS plus rho F times the AF minus AS, right? Isn't it? Okay, so AS coming from US, which is actually coming from the small u, and this one is actually coming from the Darcy's velocity, right? And the relative velocity divided by the porosity. So this is also another choice. And then of course you can also write UWP, and finally the UP. Okay, so 3, this is 3 degree of freedom. This is also 3 in 3D. This is 3, 1. This is actually 3, 1. Okay, so which one would you use? So you think about it, if you want to solve the problem faster, doesn't that make sense that we always choose the last options that have less the unknown, right? Okay, but what But why do we need to all those options? Why do we need all those options? So one of the drawbacks of using the last option is that you actually, if you use Taylor hook formulation, you will particularly see that in the Taylor hook, you have 9 degrees of freedom for the displacement field, and I would have 4 degrees of freedom for the pressure field. Now, if I compute the accelerations, where would I have acceleration for the fluid velocity? I won't even have it at the field, I'll have it at the gaseous point, right? And I only have very low resolutions, okay, for the P field, for the fluid field. Now what happens if you have an earthquake that you need a very high frequency predictions? Okay, or you have an impact or shock wave. Okay, you may not actually able to capture the high frequency behavior really well, and that's a second drawback in the sense that of the balance of mass equations. The balance of mass equations is actually written like this: the change of the displacement plus the divergence of the pole. Dows's velocity equal to 0, okay? Now, if I actually using the UW formulations, both of them are actually described at the NOx, right? Okay, so what happened to this is that if I actually use any of the 1 to 4 equations, I have something called a locally conserved balance of mass equations. Okay, meaning that your balance of mass is not necessarily satisfied only in the variational width form sense, but also satisfied it as a field. Okay, you see what I mean? Because you do have the U field and you do have the V field if you describe it at the NOx. So you can actually directly computing them, the divergent term, and to ensure that it's actually, the width form is actually conserved at every point. Okay, now, but then the UP formulations, the only advantage is that it's easy to formulate. Okay, so for that reason, we can think about using that. There are also other tricks that people use that, and then the argument is the following. For each simplicity, what you gain is the S is the easier implementations, but then you need to actually know what you lost in the predictions. So the most general one, on the other hand, the most popular one is used in the UUP formulations. This has been done in the Zingerich school a lot. A professor that used to be at Northwestern but moved to UK, and there's a Zingerich method that are honoring him for his work on the legacy in geomechanics and computational mechanics in general. And what he actually did is a UUP formulation, so let me highlight what it is there, and it should be pretty intuitive. In the UUP formulations, your goal is to write all the governing equation in terms of these 3 unknowns, okay? So you think about it, I would actually using that trick with the Dows's law in the same way I did with the UP formulations. However, the balance of linear momentum, I will split it into 2 governing equations. And I will just, without spoiling the bean, just write down the solutions. Except turning the AS and AF into big U and small u, I did not do anything for the first equation. So far so good. And for the second equations, I will simply write the balance of the balance of linear momentum only for the fluid phase. But then now I cannot cancel out the internal force that I actually apply from the solid to the fluid. And I will U double dot. Okay, so this is actually the new term. and I would have the divergence of the u dot plus divergence of v actually equal to everything equal to 0. Okay, so this is the UUP formulations. And then as you can see here, in this part, I will simply write the rho F of U dot minus U dot, big U minus small u. So fluid velocity minus the solid velocity chain. Okay? Now, one thing that I would like you to pay attention is that in principle, if I like, I can also write it as a grade K gradient of P, right? Okay, I can put this term there because they are also equal, right? But I won't do that on purpose. Why is that? Why do I not putting that? It will be equally legit. I will still have the number of unknown identical, but I would rather directly put this thing in there without using this relationship to put it there. But why is that? Why would I not doing that? The reason is the following, like what I mentioned before. I want the velocity of the fluid velocity to be described by nodal equations so that I can compute my A accurately. Okay, so I want my accelerations to be access to the nodal solutions, and I want to have a acceleration field, not the acceleration evaluated from the P that actually doesn't have a few interpretations. Okay. Now here the question is, how do I derive that? HF? And then for that, what usually happen is that people will look into the quasi-static equations to actually formulating the QF. And you can actually view it as a special case. So if I apply the divergence of the rho F EI, again, the balance of linear momentum for the fluid phase, in the quasi-static case, now it becomes 0 again. Okay, let me write it in the component notations so that I become this canonical delta, and I just take the J. So this comma J, this J are actually dummy index signifying that is actually divergence. And I have rho F G I because there's a vector for G, and H F I is also that H internal force is also a vector. Okay, so now if you take the simplifications, if rho F is actually relatively, if the change of the porosity is relative close to 0, then this term can be simplified as the rho as the porosity times the gradient of pressure. Now, if you take that simplifications and rearranging this term, I can rewrite HI as a function of this, and then I have HF equals to HFI equals to the gradient, the porosity times the gradient of P, minus the porosity times the intrinsic density of the fluid times the gradient directions. Or I can write it in the tensor notations, taking out the component, and I write gradient P minus. Okay, so far so good. So now, one practical way to put it is that then what you could actually also do is that you can write this term in terms of the minor rho F G gradient of HE, which is actually what is HE? Is the elevation hat of the gradient of the elevation hat, just like this, different vertical rotations. So what we eventually have is that HF would be equals to the rho, would be equals to the porosity times the intrinsic density of the fluid times this gradient P rho FG plus the gradient of HE term. Okay, I'm just taking out the I'm just doing some algebra trick to put this rho FG in and in the gradient. And what I will have is that I can actually write this G as the gradient of the pressure head plus the elevation head that you learned from the undergrad. And you would basically have the HF equals to the rho FG times I. Okay, I is actually just a term that used for the undergraduate solid mechanics. It's actually called a hydraulic gradient. Okay. Now, one thing that actually make it ready to apply the Darcy's velocity, and we need to apply the Darcy's velocity in this case, is that according to the Darcy's velocity, according to the Darcy's law, we have the Darcy's velocity equals to minus K dot I, K being the hydraulic conductivity, which is actually the effective permeability derived by the viscosity. Okay, now there's a minus sign there because you're moving from upstream to downstream, not the other way around. Okay, so the notation are actually high to lower number, and hence the minus sign. Now in this case, if I actually reversing that relationships, they have minus Ki minus 1 times V. Okay, I did everything here, and what I actually want, the way I think you think about it is I want to use the permeability relationship again. Okay, otherwise your governing equation would be not depends on permeability equation at all, and then it won't be correct. Okay, so this is actually for the quasi-static case. I will have the internal force of the F equals to the minus F rho F G times K minus 1 V dot. Okay, so I still need the Darcy's velocity, but I would actually have that K minus 1. By the way, in this case, what is the limitation here? Your K has to be positive definite. Okay, you cannot say that one of the eigenvalue is 0 because in this side the water is not permeable. In that case, that may happen, but then in physically it may happen, but then the K inverse doesn't exist. Okay, so if you want to actually approximate that, you can just put a very high number to it, but then the higher the number you have, the more you can actually enforcing that that impermeable thing, right? But then you would actually also come up with a higher conditional number and hence harder to solve. So if you approximate it well, you pay the price of solving a difficult problem. Okay. As for instance, an isotropic model, this is actually could be an issues like, let me say, if you have a reservoir, okay, and in between there's a layer that K is approximately equal to 0, then you may running out of trouble of formulating K minus 1. Does that make sense? Because moving in this direction is pretty easy, moving to this direction is super hard. Okay, so, but you can also argue that almost nothing is strictly speaking impermeable, and then you can assign a very low permeability there, and the inverse would be very high. Okay, so now go back to that. What I actually want is to introduce the dynamic case here, so that I will introduce Darcy's law or that are actually suitable for dynamic case. Okay, so this is actually require us to put the initial term there into our governing equations. Okay, so for dynamic case, and this is what I talk about. So for the dynamic problem, there's a two things to concern. How do I discretize, and the additional complication of the constitutive law that take account of the inertial force. Okay, So now I would actually go back to put my balance of linear momentum equation only for the fluid part. I won't combine them together. And what I would have with the new HF term that substitute back is this. Okay, does that make sense? Okay. So these two is just the partial density, right? Okay, does that make sense? These two combined, right? You see what I mean? So the partial density equals to the porosity times the intrinsic density. Okay, I simply just add all the term here, and what I actually want to do is to take out the porosity term, okay? Because all of the term now have porosity. Okay, so if this is actually the case, then what I would have is that I have rho f g k minus 1 dot v equals to gradient of p minus rho f g minus u double dot. Okay, so far so good. Now, what I actually want to do is the following. I want to write something similar to the Darcy's law. Okay, does that make sense? So what I want is to put this thing into this side so that I can write V, the Darcy's law on the left-hand side, and then whatever I have in the right-hand side, and then I can compare the quasi-static term. And that one, let me do it in 2 steps so that it's actually clear. So first, let me take the rho fg term onto the right-hand side. I would actually have this gradient P minus rho fg. Again, I'm assuming that the intrinsic density of water doesn't change. And then G times the G. And the first G is a vectorized G. And then the second G is just 9.81, okay? Plus the U double dot divided by G. Okay. Now, if I actually take it out, the K minus 1, I just time both sides by K, then what I will have is that the Darcy's velocity is actually equals to the K times I plus U double dot divided by G. This whole thing here is actually the hydraulic gradient. Okay, the aeration head and the pressure head. Okay. Now, if I actually write it like this, then what we would eventually have is that V is actually equal to minus K dot times I, hydraulic gradient, plus AF divided by G. Okay, G is just a constant, okay? And this term is actually the term nil for the Darcy's law that you need to consider. Okay, you see what I mean? Previously, V is simply equals to K times I. Okay, now there's an extra term. Okay, so if AF is very high, what happens? Your velocity will be driven by the inertial force, but not by the sea gauge, isn't it? Okay, you're absolutely, how does the AF move actually is more important than the relative movement between the solid and the fluid. Okay, remember that fluid itself also have dynamic behavior. So fluid, in terms of, in particularly in the case when it's water or fluid, they are actually quite heavy, right? So if you have a tremendous amount of inertial force, that would actually, of course, lead to a substantial amount of accelerations. And that accelerations would actually, of course, change the velocity, right? Now, and then this I is actually coming from the relative motions between the solid and fluid. Okay, so this is actually the extra term for dynamics. Okay. Now this also make it a little bit harder to model. Okay. Now, but the UUP formulations have one big advantage, like what I said, because you directly model the U, right? Okay, you can directly actually understand what kind of discretization you need by actually calculating a wavelength. Okay, does that make sense? Now, in general, if I have a wave that look like this, okay, so how many elements do I need to capture this? Let's say just sinusoidal wave. Okay, obviously, if you only have two nodes here, so what will happen if the wave propagate to this point, toward this element? It won't able to replicating that, and then you will see an instability that actually occurs, because the energy is still there, but your file element cannot actually able to replicate this pattern. There's also another possibility. It's like a shock. Okay, so there's a jump there, and then this jump is moving in time. Okay, and your final element is actually have a discretizations that look like this. Okay, so but then your exact solutions is actually having a jump here. So what will happen? What do you think would happen? If you actually solve the final elements or without doing anything special, you will notice you have something like this. Okay, if you don't have enough element, not exactly in these discretizations, and you won't able to capture this. Okay, you can use a technique called artificial viscosity to filter out this, or if you use FFT solver, this is actually called the Gibbs. This is actually called the Gibbs phenomena, and you need to do something special to allow you to capture the shock, or actually render the shock into some shock gradient. Okay. Now, there's another case, okay, for the UU formulations, in which case I won't talk about it in great details, but what I can assure you is that you still need to somehow put the permeability in your formulations, and it can also be easily generalizing to compressor flow. For the UP formulations, okay, one general assumption is that, let me put it this way. In the UU formulations, I won't talk about the details, but there's a few strategies here, is that you often assume compressible flow instead of incompressible. And you often write the P as a function of the gradient of U and the gradient of big U. Okay, which makes sense, right? Okay, you see what I mean? So what is the gradient of U? Sorry, not the gradient, the chase of the gradient, which is actually the divergence. Okay, so volume to pressure. So you basically keep track of the volume change of the material, and you estimate either the P or the P dot, or both. Okay. Now this is another UP formulations, and what the UP formulation did is the following. What people generally assume is assuming that is like what we talked about before. AF minus AS is actually equal to 0. Okay, so I only care about the rho times AS term. Okay, and then I take out this term. Why do I do that? It's just for simplicity. Okay, so and of course that will greatly simplify the equations, and in fact you lead to something that are really easy to handle. This is just the effective stress times Pi plus rho G equals to rho U double dot solid, and then divergence of U dot plus divergence of V dot equal to 0. Okay, this is very simple, right? I just simply add an additional term in the second order term, isn't it? Okay, and the balance of mass doesn't even change. Okay, so there's this benefit on doing that. but you may still come up with additional term for the P, right? Okay, why is that? Because I will still have the Darcy's velocity that are now equals to the minor K times the hydraulic gradient times the U double dot divided by G. Okay, now this is actually also a big problem. Okay, so because I actually, if I want to have the UP formulation, this is for the small p U, not for the big U, right? Okay, but now this governing equation is for the fluid velocity, not the solid. So what the people did, again, you just take the easy route. I'm assuming that the whole thing in such a short period of time is actually undrained. Okay, so if things are undrained, then what happens? Then U equals to small u equals to big U. Okay, if small u equals to big U, then small u minus big U, or your big U minus small u is both 0, right? But I can also replacing it with just the small u divided by G, right? Then I would actually able to maintain my UP formulations, because this one would still be the pressure gradient. Something will be a pressure gradient term plus a constant, okay? So I have two terms, the pressure gradient term and the elevation head, but the elevation head is constant. There's no unknown there. I'll just end up putting something in the right-hand side, right? Okay, so this is a function of the gradient of the P, and this one will be U. So this Darcy's law is represent as the two fundamental unknown. I want to solve the P and the solid displacement small u, right? Okay, you see what I mean? Then of course, is the whole thing always undrained? It's not. They don't actually need to trap and move together. Okay. This is also for practical reasons. In a very short period of time, usually if the permeability is very small, not very slow, you can assuming that the displacement between the fluid and water are not that different, okay? Because they're trapped, okay, in a very short period. There's not enough time to see gauge. But of course, that would be approximation, so you always need to remember that the UP formulation is not as strongly recommended for dynamic problem as the other problem. But the benefit you have is just an easier discretization and cheaper for the simulations, okay? You may not see that much difference if you want to do a homework with 10 elements, but if you want to build a reservoir simulator for ExxonMobil, for example, you literally deal with at least a few million of degree of freedom, and then having 7 degree of freedom per nodes versus 4 would actually make a big price difference in terms of the solver. Okay, so let me put the remark, because this could also be a good final project if you actually are interested, just like the unsaturated porous media. In the UP formulations, you would actually need to exact problem for transient or for static problem that only have first order derivative. It will be only approximate dynamics. It won't be capturing the external inertia force actually that accurately, which could be a drawback, assuming AS equals to AF. Is actually both a good thing for simplification, but also actually it could also be an issue. Okay, so for these reasons, for this AF equals to AF, they are sometimes used for earthquake simulations. Okay, why do we doing it for earthquake simulations? Why is it okay? It has to do with the mechanism of the earthquake. Okay, so most likely if you have earthquake, what happened to the frequency? What is the frequency of an earthquake? What is the frequency, or what is the wavelength of the earthquake? I'll put it the other way. Okay. So I think it's in terms of hertz, right? Okay. So what happened is that in this band group, or in this relatively low frequency regions, the UP formulation doesn't generate that much error per se, even with that simplifications. In particular, when the permeability itself is very small. Okay, for clay material or whatever. Okay, you can actually measure the pressure build-up quite well, and then you can predict the earthquake, at least qualitatively. However, you will not use it for the following case. One is for shock. Okay, hypersonic thing, you probably definitely don't want to use a UP. You need two equation of state, in fact, or at least you need to have the nodal representation of the displacement for the fluid and the solid. Okay, in this case, the local representations or able to obtaining the field become crucial. And also for stimuli, for busting, and then also for impact. Okay, for things that create a significant impact, or for things that actually have very high frequency response, or even a shock wave, these formulations is actually not really recommended, the UP formulations. Okay, now there are other ways to deal with it, like using the discrete Gillikin method. Do you know what is Gillikin? Discrete Gillikin method. Basically, the elements are not joined together, and then in between the element, there's an additional term to bind them together. Now, this often been used for model dynamic case, but then you have to pay the price of solving a more expensive finite element. Okay, because now, if you have 3 elements, 1, 2, 3, 4, 5, 6 in 1D, you have 6 nodes, versus in the classical phase, I will 1, 2, 3, 4 nodes. Okay, you see what I mean? Because these two are these 1, 2, 3, 1 and 2, 2 and 3 share element, both share 1 nodes, but in the DG you don't share any nodes. Okay, so that will lead to another type of difficulty. But the price you pay is that because you have these discretizations, so you have a more opportunity to replicating those jumps that you need to model the shock wave. Okay. So let me take a break here. Let's come back at 11:30 so that we can finish the discretizations, and then you can see the matrix form, and we can perform the model analysis for the dynamic case. And then we will conclude the dynamic formulation. Okay, so anyone interested in doing the dynamic for the final project? You can, if you solve the dynamic problem, this is your choice. I would suggest that you simply try to propagate a sinusoidal wave just to see what happens. Okay, and that's something you can easily see. If you model only compassive wave, then you will see a secondary wave that. So in general, you know, in the solid mechanics, you have one wave, and that wave is simply, what is the wave speed for compassive wave? The square root of the Buck modulus divided by the density, right? Right. Okay. So the more incompressible it is, the faster the wave speed. If it's incompressible, it immediately reaches to the other end. Right? Right? Does that make sense? Okay. Now, if your Buck modulus is finite, it will take time for the wave to propagate from one side to the other side. That speed is actually related to the k divided by the square root of k divided by the rho. But now for the porous media, there's a 2 different k, right? Okay, there's a solid and there's a fluid part. So you will observe another wave that compressive rate that are actually coming, and that the second one is much slower. So there's a lot of application to that. You can using that to detect what's going on in the fluid, how many fluid you have, or for acoustic reasons. Okay, so this has been active research. In fact, one of the Beals medalists, there's a Beals medal in honor of the Beals contribution to the pole elasticity, and one of the work from Berryman is actually focused on that secondary wave. Anyway, I'll not take further time, so let's come back in 9 minutes. Okay, so I just want to talk about another part of the constitutive law. Okay, so have you guys taken a file element with the dynamic case? Do you know what is the matrix form look like? Basically, M, a matrix with the U double dot plus C, U double dot, sorry, U with one dot plus KU equals to F, right? Or the right hand side. Okay, this is a 1D dynamic case. One-dimensional dynamic case. So this is the inertia force. And this is actually called the damping force. And this is actually still the stiffness. Okay, it's coming from the elastic storage of the material. Now, this is dissipative, meaning that without this damping force, the system would actually move forever. You can try to simulate a 1D short wave. If you actually put the D equal to 0 here, then this pattern would just keep moving, bouncing around each other forever without degrading, okay? Because there's no mechanism to dissipating the force. The first order term can happen physically or it can happen numerically. People often add some dissipation force for the dynamics. The most famous technique is called the alpha method, which is actually, you probably heard only from finite element. What is alpha method? Is that you introduce the dissipation by considering considering the change of the accelerations, and add a term there that actually introduces the damping. Another case that often happens is that the material itself materially also have damping effect. Then we don't actually need to add any artificial damping if the damping is sufficient. So here for the solid, we talk about the constitutive law for the fluid, basically the dynamic versions of the Dawes law. Now I want to talk about the solid constitutive law. In the quasi-static case, the stress is actually related to is actually a function of the elastic strain, or sometimes just the strain. Okay, does that make sense? Now, in the dynamic case, or actually even in the transient case, what I actually want to do is that I want to write the stress not necessarily as the functions of the string itself, but also the strain rate. Okay, does that make sense? Okay, so I want the material to have different stress if I'm loading it in different speed. That's essentially what I'm saying. Okay, even though they have the same strength, if I have different strength rate, I want it to have different stress. Okay? Do you get the intuitions? The simplest case is actually called Kelvin's viscoelastic solid. Okay, so in a linear case, it takes a very simple form. The effective stress is actually equal to C double dot epsilon plus D double dot epsilon dot. Okay, C is actually the stiffness matrix, right? Or what is D? D actually governing the damping force, okay? Or the weight dependent force, okay? So now, if you load something in very high strain way, then which term will matter? Then the D term will matter, right? Okay, this is very good. Okay, if you load something very slowly, okay, extremely slowly, so the epsilon dot is approximately 0, then we get back the original linear elasticity law, right? Okay, but how do you categorize fast and slow? It depends on the D term and also the permeability term because it would also affecting the coupling, right? And people using that a lot also in the context of model equation of state. You will add those terms, or in NPM, this is often happen. If you want to model explosive, then you need to have two terms that in the very high loading regions, it behaves like a liquid. So you put all the thing in D, and then in a quasi-static case, you put the thing in C, so that when the string is dominant, you actually have a stress. Now, this is actually have a particular consequence of that stress, okay? What it means is that the string alone doesn't give you the stress, isn't it? Because the stress is not only depends on string, but the string wave, right? So what happens if you load a material very quick and you get one stress, and over time, what would happen? Okay, so imagine that you actually passing the material really hard, okay? Or actually maybe I do the opposite. I apply retraction there, okay? So what happened? Initially, what will happen? Okay, I actually have to balance the material with another opposite traction, right? Right, if the material doesn't move, okay? Now, where does that traction come from initially? Initially, it will come from the D term, right? Okay, because let me discretizing it a little bit. If I'm discretizing it as epsilon n plus 1 minus epsilon n divided by delta t, this is one way of discretizing it, by the way, then what will happen? What will happen? So I will have the stress equals to C double dot epsilon n plus 1, okay? According, if I use the backward Euler, plus the D epsilon plus 1 minus delta D minus D epsilon n delta T. Right, isn't it? If I just do a first order, and then what I will have is that C plus D divided by delta D times epsilon n plus 1 minus D divided by delta T epsilon n. Right? Okay. So what happened in the very first step? Epsilon n is actually assumed to be 0. Okay, then what would happen? I will have epsilon n, and then, right? You see what I mean? But then what happened to the next step? The epsilon n, so if epsilon 0 is actually equal to 0, right? Then epsilon 1 would be equal to C minus D delta T inverse times epsilon times this stress, right? Does that make sense? For the first time step. Does that make sense? I'm just inversing this term. Right? You see what I mean? You get it? Okay, what happened to epsilon 2? What happened to epsilon 2? It will be C plus D divided by delta T minus 1 times what? I just need to do this epsilon 1, sigma, and then what? Now I have epsilon 1, right? So I put it on the other side plus D delta T epsilon 1, right? Okay. So what happened to epsilon 3? See, 1, 2, 3 is the time step. I just keep doing what I'm doing, right? Okay. So what you will see in the case of the loading. So I guess the other questions is I guess the questions I want to ask is that what will be the loading history of the epsilon versus time? Assuming that is let's consider it as a 1D case. Okay, over time, do you have more strain or less strain? It depends, right? Depends on what is the eigenvalue of C. So depends on, in 1D, that would depend on what is the value of C and D and delta T, right? Right, okay. But what you actually would see is a weight-dependent relationship between the stress and strain. They're not one-to-one anymore. And then for different loading, you have a different weight. Now, this weight-dependent introduced by the Kelvin's viscoelasticity is different than the weight-dependent effect introduced by the hydraulic diffusions in the following sense. The hydraulic diffusions, the weight dependent is triggered by the permeability and the movement of the liquid itself, and it actually depends on the gradient of P. This one actually still depends on the sigma, not the gradient of sigma. Okay, so there's a different spatial effect related to that, although both of them introduce weight dependency. Okay. So when you want to model biological material, the solid skeleton itself is often also weight dependency. The liquid also introduce weight dependency, and when you solve the inverse problem, it's important to separate one from the other. Otherwise, then you would actually see a very different effect. In the sense that if you actually have a hydraulic introduce the diffusion-dependent weight dependency, it would have a size effect because you actually depends on the dust velocity, which is related to the gradient of P, which actually the gradient is the spatial derivative, right? Whereas here, there's no spatial effect. If you actually have a very big material and very small material, you will have the same Kelvin viscoelastic response. Okay, so there's a very subtle but difference. Both of them introduce weight dependency, but they introduce weight dependency in a different way. Okay, so there's our other viscoelasticity model, but here we are not doing solid mechanics, so I just leave it like that. I just want to give you the simplest governing equations that I could find. Okay, and then I will put it into the UP formulations. So I will just use the UP formulations as the motivations. So go back to the Sinkerich. I think that when Professor Sinkerich passed away, there's a memorial article on the heritage of Professor Sinkerich that actually document all the different UP formulations. I recommend that you take a look if you are really interested. But now let me go back to these formulations. So the width form actually would be simply obtained by integration by part, and you're probably already familiar with hear it about 1,000 of times right now, so I would not repeat. It's actually identical except that I actually add this new term here equal to 0. okay, and the same balance of mass. Now, the trick here is the following. I want to substitute this now with the viscous term so that the material will actually reach a quasi-static state somehow, or actually able to model the rate-dependent effect. So from the balance of linear momentum, I need to use the effective stress theorem, and if I'm using this, I will lead to this term. Now the first term is just coming from the inertial force, second derivative of the nodal displacements, and then the term here, this is a symmetric term that gives us the dynamic inertia force, and I have the second term that are just like our quasi-static counterpart, and then it's also applied to the B matrix, but this is actually for the first order damping term. So first order this velocity term, and then I will have my classical stiffness term, plus the G matrix times P equals to F external. Okay, so this in the structural dynamics we often call it K term, and this one we often call it D to stand for damping, and this is actually just the mass matrix. Does that make sense? Now I want to ask you a question. Is NT rho n, is that integral? In general, is it positive definite? Is it positive definite? Or is it singular? NTN, very simple. Is it positive definite? Generally speaking, it's not guaranteed to be positive singular. In fact, it could be singular. Okay. Why? You can try to do a numerical calculations and see what happened. Okay. Now, if you actually look into the individual term, what we have is very similar to the structural dynamic term. I get the md double dot times the damping times the velocity times the stiffness times the displacement plus gp, the hydraulic term, which is you need for pole mechanics, pole dynamics, and then the F external term. Okay, for the Darcy's law, for the balance of mass, I will have GTP dot plus the E matrix, which is actually the gradient of the n times the Darcy's velocity equals to GEXT. Okay, so what is this term? This term is actually the Darcy's velocity, which in our case is simplified as the gradient of the P times the gradient of P divided by the intrinsic density times the elevations head times the solid density, solid acceleration normalizing by the gravitational constant. Okay, so what we would eventually have is I will have that GT d dot minus F minus the integrations of what we had before in the quasi-static minor 1 divided by G VTKN D double dot GXT. Okay, now this term is just here, this is already exits. This term is actually coming from here, and this term is coming from the new inertia force affecting the downside velocity. Okay, and then this term is putting into the G external side because it's a constant. Okay, you see what I mean? So G, the vector G divided by the G just give you a normal vector in the vertical, in the direction where you have the vertical, if you're on Earth. Okay, you see what I mean? The direction that pointing towards the center of the Earth. Okay. Now, what happened is that the balance of mass will give us the following term. If we call this new thing that are pretty weird, we call it P matrix. Then we'll have the P D double dot plus G T D dot plus the omega term that carry the permeability term times the G external pi. Okay, just adding the new elevation head there. Now, as you can see, what it actually happened is that compared to the transient first order time, I simply need to add the P matrix there and the discretization for the D, and I also only need to add the D term there, and then I'm done with my job. Oh, also the M term. Okay, and then I was done with my discretization job, right? Okay, in practice, sometimes people would not directly using this term, but using the lump mass. Okay, what is the benefit of using the lump mass? So do you guys know what is a lump mass matrix? Okay, lump mass matrix is a diagonal matrix that actually lump the mass of each row. Okay, it could be argued by simply row sum, or it could be actually arguing from a variational principle. It would generate different type of lump mass. Okay, in general, if you use lump mass, your discretization is not consistent, and the drawback of doing the lump mass is that you won't actually able to capture the wave exactly. Okay, so your material wavelength would be affected by your discretization and introduce some error. Okay, although if you refine the max, you can reduce the error. But compared to the consistent mass, you lost the consistency. If you're using the actual thing, it's called consistent mass. Okay, and then there are also another variation. It's called higher order mass. If you look at Professor Tom Hughes' book, basically is to introduce the higher order term to constituting the mass to actually filter out the oscillation that may otherwise occur. Okay, in the lump mass case, if you actually results in a diagonal mass, what is the benefit to it? Is that diagonal matrix are very easy to inverse, right? Why is it very easy to inverse? Because it's diagonal, right? So your diagonal value is already the eigenvalues. So what it means is that you just need to independently inverse it one by one, and that's it. Okay. So in fact, in the solid mechanics, you lead to a matrix phi update simply because you use a lump mass. Okay. Now here, in this case, it may or may not be practical, but let me put the equation together. Eventually, what we have is this interesting system. Before I actually applying the new math or whatever alpha method to do the time discretizations, I will have the second order term of P that I never use. Do you see that? P double dot I never use in the matrix, right? Do you see that? And the D, where again, it's actually pretty interesting. The P dot is again never utilized. Okay, only the D dot and the D double dot are used. Plus this classical matrix that we encounter many times from the UP formulations. Okay, so if we call this M and this product space X, we come back into a system that have this M X double dot plus CX dot plus KX equals to F. Okay, so have you seen that system before? When the structural dynamic course, you're probably already saw that, right? Okay. Can you do eigenvalue analysis to it? Can you do modal analysis to it? Do you guys remember what is modal analysis? You compute the eigenvalue and the eigenvector. The eigenvector gives you the mode, right? And then you can reduce the dimension. Right now, can you do it? George, can you do it?
Yes.
Under what case would that be yes? C is 0, yeah. If you have damping, it won't work. Simply, you can think about it. If you have damping, you actually would not have the same modal solution. It will change over time. You actually go back to quasi-static. But if you take it out, that you have mx double dot plus kx equal to f, you can solve what is called a generalized eigenvalue problem. Basically, put the m minus 1 k, and then you can actually have x double dot plus m minus 1 k times x equals to f, and you can do a modal analysis to reduce the dimensions. But in general, this route is actually not used that often. Okay, so, but one thing that are actually quite important is that to observe is that P dot is not used at all, and P double dot is not used, and P dot is also not used in these formulations. If you want to changing it, is it possible that P double dot is actually used? You could actually think about a way to using it if you can actually put back the inertial force of the Darcy's velocity, isn't it? Right? But in that case, your P matrix will become 0. Do you see that? Do you see that? Because your Darcy's, this thing coming from the Darcy's law, okay, coming from the A divided by G term, but because you're actually assuming then the AF is equal to AS, that's why you have the P term. But if you put back the fluid term, then you will have a block diagonal matrix instead, which in some case could be a nice property to have for the mixed problem. Here, as you can see, even if you're formulating it, you won't actually have a diagonal matrix, even for the fluid part, because you cannot actually emulating this, right? Do you see that? This whole row is 0, okay? So now it doesn't mean that it will be a problem, because you're never solving this as is. You still have to use the time discretizing to rewrite the D double dot and P double dot and D dot P dot into something else, right? So in your solid finite element course, you can actually use the first term as the prime variable. You're discretizing the A and you're discretizing the accelerations, or you're discretizing the velocity, or you're discretizing the displacement. Okay, both are equally valid, okay, but you actually need to think about it carefully. And there's also another thing that are very important is the role of the noise. A lot of time, the forcing function F there would have some noise. Okay, but the noise on displacement and the noise for velocity and then the noise of acceleration will have different effect. Okay, so this is actually something that are very detailed, but you need to pay attention. Let me give you an example. Let's say I have a accelerogram that look like this. Okay, so far so good. So this is time, this is my accelerations, and then this is the forcing function that I want to introduce on my F external, or I want to prescribe some nodes that have this A. Okay, now let's say I make an error so that the accelerogram is offset by actually measuring something a little bit on top. This is what I get. Okay, so far so good. Everything is shift by a delta A, okay? Now what will happen to the velocity? What will be the velocity look like? Or let's assume the sinusoidal, right? If I have a sine t, then take the derivative, I get cosine, right? Okay, so now, but if I off-shifting a little bit, so what would happen to that cosine? I would instead have a function that look like this. Right? Why is this? Because a constant A lead to a linear changing A, right? Now what happened to the displacement? The displacement, if you have a sine, then you take a cosine and take another derivative, you get back the sine, right? Okay, now, but then your background will give you a quadratic thing, and then you will have this term. Okay? So if you actually want to predict landslide or in using accelerations, and you have some offset, and then you will get a quadratic term, and you're using it to predict the displacement, it will be completely wrong. Okay, simply because of the noise. And that wrong is actually integrate. So it actually, you can see that, okay? You see what I mean? If you actually integrate with displacement, you will see that. But that could be very important issues on the forcing function part for modeling or earthquake. You want to model the earthquake, sometimes you want to know, okay, after the earthquake, what is the permanent displacement, and then your accelerogram have noise. Okay, and then that noise is not usually just a shift, but a random noise. But then the random noise is integrated twice. Okay, so the displacement prediction is actually very difficult without identifying the way to identifying the noise. Okay, you see what I mean? Or put it the other way, if I know there's a noise, and in fact I want to apply some kind of filter to take out the noise, okay, will my filter work? I may actually accidentally, I can actually assume there's a offset or whatever. But if I actually removing too much, then I would actually also change the pattern significantly. Okay, you see what I mean? But unfortunately, well, maybe not unfortunately, the mechanism is that you're very likely to get a lot more accelerogram than a lot of GPT, not GPT, GPS informations that are over time. So if you want to model the earthquake simulation, the reason that then you would both use an accelerogram, but you would also use the GPS positioning to actually help you to detect the noise. Does that make sense? For earthquake predictions, because then the GPS prediction before and after the earthquake will give me the displacement, right? From the displacement, you can see whether your accelerogram is compatible to that displacement. At a select point, then you have a way to actually filtering and then get the right residual. So this is actually some practical tips that are often used, but go back to the theory part on the dynamics. Okay. So the C here, the one I want to also mention is that C actually have a two-part, the D and then the GT00. D is actually called the viscous damping. In fact, if you model 3D printing of concrete, you need to model the viscous part very importantly, because the deform is not related to the stress, but over time you would have a stress relaxation and it change over time. Okay, so generally speaking, the D would be more important, but then this D is actually due to the Kelvin linear viscoelasticity model we use, and G is actually the transient term introduced by the slip gauge. Okay, if you look at the term, it also have a different implications. And K is actually the same as the previous K. Okay, so far so good. Now, if I use the A form, I just want to go through it very quickly. Then M would be equals to n plus 1 plus C V n plus 1 plus K x n plus 1 plus F n plus 1. This is just the time discretizations, whether it's solid or porous media is identical. And then I write M plus alpha delta T C plus beta alpha T squared K times A n plus 1 equals to F n plus 1 minus F x n V n A n. And I won't actually specify what is F, the small f here. You can do the derivation yourself. Now, let me ask you one thing. What is alpha and beta? What is that scheme called? It's called the Newmark scheme. Okay, so you probably again heard about it from the structural dynamics. And what is a good number for alpha and beta? Okay, what would be the good number? Now, let me show you one similar case, and then you can actually try to make sense out of it. Okay, let's say that Vn is actually equals to let's say I use backward Euler for everything. Vn plus 1 equals to un plus 1 minus un divided by delta t. Okay, so far so good. And an plus 1 is actually equals to Vn plus 1 minus Vn minus delta t. Okay, so far so good. Now substitute this into this, what do we get? Okay, let me write it out. I will get un plus 1 minus un divided by delta t squared, the first term, and then minus un, right? Plus un minus 1, right? Does that make sense? So I have un plus 1 minus 2un plus un minus 1 divided by delta t squared. Okay? Sometimes this is actually used in AMD. Now, what does it have to do with alpha and beta? Do you see that? In this case, if I use this scheme, what is the alpha and beta? Or maybe I do a little bit like, okay, so at squared an minus 1 equals to plus 1 minus un plus un minus 1. Right? Okay, so So what happened? Oh, I can write it in the other way. Okay, I can write it as the following. Un plus 1, right? I can write in the following. How do I write un plus 1 as the functions of an? Right? Etc. etc. Anyway, so long story short, you can actually review it from the Newmark scheme, and alpha and beta are actually cannot be chosen randomly. Okay, it has to be chosen. It is only conditional stable with a finite set of number, and one has to be. Otherwise, you will lose the stability. Because of the limit of time, I won't actually calculate the amplification factor tensor. Amplification factor again. But if but it will be very similar to the first order term. You need to compute the spectral radius, and then you need to actually find out what is the conditional number set of parameter. Okay. Now, out of all the Newmark set parameter set, there's only one set. There's a subset of them preserve energy. Other one that other method may dissipate energy or even unstable. Okay. But in practice, in some applications, you want it to preserving the moment and the energy by choosing the right parameter. That has been discussed in Warren and Simo in the moment and energy preserving time integrator. If you're interested, you can take a look. But in general practice, you would actually expecting your numerical scheme also have some numerical dissipation just to get you a stable response. Okay, for other applications, if you have a multi-body dynamic like modeling the solar system, yeah, or maybe three-body problem or whatever, then you do need to actually model it so that the energy conserved, because otherwise the trajectory of the planet moving along with the star would actually keep changing because of the dissipations. Okay, so go back to that. Let me actually mention about the modal decompositions. So it's possible to do a modal decompositions if you can find the mode, okay, for the linear problem. So let me consider, and this is actually also helpful for us to analyzing the stability of the system. So this is actually not so different between multi-physics problem and a single physics problem. I have this problem, okay, because I'm actually now using the spatial discretizations with the finite element. So this is actually the ODE, okay? Do you guys see that? It's a multivariable ODE, okay? So it only depends on space, there's no time derivative. So it only depends on time, there's no spatial derivative anymore. If I actually computing assuming of eigenmode that look, or actually solutions that look like this. So this is actually the mode shape, and this is actually the lambda that change over time. I take the first derivative, I would basically lambda this. I take the second derivative, I would get these equations. So far so good, okay. Now I substitute back into the governing equations that are in the previous page, or maybe I substitute it here. So what I would have is that I have a lambda square times m plus lambda c plus k times the mole times the binary e lambda t equal to 0. Okay, as you can see here, now I have one extra term, the m, that in our previous derivative transient analysis we don't have. Now, how do I find what is the lambda? How do I find all the lambda mode? Now, if you put this as the like eigenvector. What I actually want to know is to check under what case would the determinant of the direction of this term actually equal to 0. Okay? You see what I mean? So in the spectral form, what I would have is that I will have a lambda square m plus lambda d plus k plus g times lambda square d plus lambda gt times this equal to 0. Okay? Sorry, the determinant of it. Okay, so far so good. So if I actually find out what is the lambda, how do I using it? How do I using it? If I successfully find all the lambda, what does that mean? What does that mean? You will find the mode shape, right? In this case, I would also able to find this because I know this is not equal to 0. So after I substitute it back, lambda with a particular value, this thing will become a matrix that I know all the term, right? I already know what is m term, what is c term, what is k term. The only thing I don't know is lambda. If I solve the lambda, I will know what is a lambda term. If I solve what is a lambda term of the matrix, from that I can find out what is the corresponding eigenvector. Okay, sorry, maybe not eigenvector, but the vector that actually lead to this equal to 0, right? Because this term is a constant everywhere. So I can decomposing it in multiple mode, and if I actually want, I can reduce the dimension of the problem, but by taking out some of the mode that are associated with very small lambda. Okay, so in general, the number of lambda would be actually equals to the number of equations. So if I find a lambda, it won't give us any discount. Then of course it only works for linear problem. Okay. So the final thing I want to talk about is to giving a concrete formulation of the time integrations. That one is not new, and you should have learned it from the structural dynamics class, or you can actually learning it from maybe the second part of the file element. I don't know what is covered these days. So the generic term is the following. Given xn, x dot n, and x double dot n, and maybe sometime even x minus 1. Find the xn plus 1, xn plus 1, dot, and xn plus 1 double dot. Okay, does that make sense? And this somehow implies that you may even know xn minus 1, because this term could be actually depends on the previous time step, but the previous time step. So what the Newmark scheme say is the following. Xn plus 1 is actually equal to xn plus the delta t of Vn, which is actually the same as the backward Euler, but there will be a higher order term, x delta t divided by 2 plus 1 minus 2 beta an, plus 1 minus 2 beta t, 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 plus beta delta t squared an plus 1. Okay, so these two terms are actually for the new second order term. And if you do it for the Vn, do the similar thing for the Vn. Vn is no longer only depends on the previous time step, but of course depends on gamma, which is actually depends on the weight average of an and an plus 1. Okay, alpha is the weighting factor, depends on how much you want to averaging the accelerations for the new time step or from the previous time step. Okay, and the same for beta, but then the beta effect on the x is actually more indirect. It's a second order effect on how do you want to take account of the new accelerations compared to the old accelerations. Okay, you can try to implementing that. Is actually just like 1 minute, and you can actually try play around with beta and gamma, and you will see that if you pick a random number, if it's unstable, the thing will go to infinite really fast. Okay, this is also something interesting to know. And like what I said before, you can actually perform a static condensations, and then you can actually get Gaussian equations. And for the dynamic case, also one thing that important is that if the inertial force is actually go to 0, you should get back the original quasi-static, the transient consolidation problem. There's also a terminology term. Basically, people say consolidations refer to the one that taking out dynamics, although sometimes people call it dynamic consolidation, which means that you include the inertia term. Okay, so again, there's not that much new on the theory part except putting the inertial force, but then the dynamic thing in a grand scheme of things require you to do two surgery on the incompressible model. One is to put the right constitutive law relationship to it, both for the solid and also for the Darcy's law, including the inertial term. Second, you need to have care on how do you make the discretization feasible. And the problem is not that you don't have choice. The problem is that you have so many different choices. Okay, again, for the short wave, or actually for something where the fluid movement is very important, I would suggest that you put either the Darcy's velocity or the fluid displacement or the fluid velocity into the nodal solutions. Okay, for other things, you just want to get some effect of the liquid, but then and you're actually loading it in very low frequency loading. I think that the UP formulation can give you good approximations, right? But again, in generally speaking, the lower the permeability it is, the harder to solve the consolidation problem. And the inertial force also making the problem to solve much more challenging. Okay, so there's a few things that could go wrong. You pick the wrong Newmark scheme, you have the wrong discretizations, or you try to solve, or you have to make sure that your forcing functions wavelength is actually accommodative to, is actually compatible to the mesh that you have. Okay, you see what I mean? And the damping is actually in practice is your friend. The damping would actually provide you the conversion into a quasi-cyclic problem, and then the system will eventually that if there's a damping. When I say that, it means that it reached the steady state problem. Okay, so I think that, yeah, that's all for the dynamics thing. Any questions? So I would send out an email to request for extra time for the for one more lecture and for the final presentations. Does anyone want to have so basically usually what I did is that I will use the final time slot to have the presentations, which is usually the same time but in May after the reading period. So is there anyone have a time conflicts?